MacBook Air. The description is no power. First thing we want to do, like we always like to do it before we connect power to the device. We want to first confirm what state the device is in. Take out the back cover. To take the back cover out, I'm using a P5 pendulum screwdriver. Now, another thing I always also like to do is I also like to guide my screwdriver so that there is no scratches on the back of the device. So I use my finger to guide the screwdriver like this. So that way I prevent the screwdriver from slipping to create, I mean all of the scratches that you see, for example. Okay, the cover is out. This is a MacBook Air 13 inches. Because of the JTAG connector, we can confirm that this is 2015, 2017. Is that?
Confirm also someone tried to attempt
Uh, I can't pick that up with this looks very decent. It doesn't look like it's been attempted at all. We seem to be the first to open up the device. It doesn't look like all of the screws are intact, all of the cables are properly connected. Yeah, it doesn't look like it's been attempted before. Okay, so this looks good. So since there is no sign of liquid, okay, looks like there's a bit of okay. So I see a bit of liquid. I see a bit of liquid. Let's see what that's something like that. Okay, so the next thing we want to do is now, it doesn't look like there is any threat from connecting the charger. So now let's connect our charger to see what we are dealing with. So this is going to use a MagSafe 2. 45 watts will do, but then if you don't have a 45 watts, if you have like a 65 watts and an 85 watts, that still can be used. It's not a problem. So yeah, we MagSafe 2. Let's see what we have. Charger is connected, and there is a proper communication, which is we saw that the charger moved, changed from green to amber, which is exactly what it should do. And then so there was a slight delay also after the charger was connected and before communication was established. That is also a way we can confirm that the charger we are using is an original Apple charger. Okay, so first thing we have established, there is communication between our charger and the logic board, and that also tells us that the sys1 wire circuitry is working, and also that also tells us that a section of the SMC is also working. Partially the SMC, I would say 40 to 70% of the SMC is working. Another way we just want to confirm that is now let's see what we have on our PP bus. Now we will not worry about PP3V42, and then we will not worry about PPDC in. PPDC in, it's the main is the primary power rail that is generated when the charger is connected. Right now, we will not worry about that. Why? Because we see that there is communication. If PPDC in was not present, there will be no communication. And also, if PP3V42, because PP3V42 is a critical rail required for the sys1 wire to be active, which is for the indication we see on the charger to be present, the PP3V42 rail must be present. So after PPDC has been generated, then PP3V42 being present, with those two rails being present, that is why we have this. If those were not present, we will not have the communication that we see on the charger. The light we see on the charger will not be present. Can you see the light from there? Yeah. Okay, fine. So the next thing we want to do now is we want to see what we have on our PV bus. Now, to get accurate measurements on our PV bus, we'll have to disconnect the battery. So battery cable is disconnected. Um, and then another thing we also want to do is sometimes the machine might be stuck in a particular mode. So, and disconnecting the battery will help you remove the machine from that mode. So, before we do any type of measurement now, after the battery has been disconnected, we want to remove or disconnect the charger from the device and then connect again. And then this is a MacBook Air, and which is it requires really low power to function. So even without the battery connected, you can use your charger to power the device, and then the device will work just fine. So I mean, I had to mention that because in some devices, for example, like the 16 inches, for example, if you connect the charger and then without the battery support, the device may not power. It may boot loop. So it's important to note that. So, but with a MacBook Air, because the power consumption is very little, you do not really need the battery to be present for the. Without the battery, the machine will still work fine with the charger only connected. Okay, so the next thing we want to do now is and then just to mention, just for mentioning, the battery plays the role of the battery here basically on this device would be to provide power in absence of the charger. You understand? So the charger powers the device, and this also charges the battery, and then that the battery will be a secondary power supply in a situation where you have the primary power supply and not being present. So that said, the next thing I'm going to do now, let's connect. So the reason why we disconnected the battery and also disconnect the charger, it's so in case the device is stuck in any type of mode. For example, although an indication of that, if it was stuck in reset mode, an indication of if SMC was stuck in reset mode, what would happen is when the charger is connected, it would not move from amber to it would not move from green to amber. It's just going to be stuck on amber, and that will be whether the battery is fully charged or not, and that will also be whether the battery is connected or not. But I mean, from what we saw, it doesn't seem that that is the case. So let's now connect the charger again and see if we have any different reaction. Okay, now we have a different reaction. So this is good. So what we want to do now, let's just see if the device goes. Okay, let's see if we have devices posting. Device doesn't seem to be posting. Okay, though we have a fan spin, but no post. So what we want to do now is let's force the device. Let's force it down. Try to shut it down. Force off. Let's try it again. See what happens. Try to power the device again. And the device doesn't seem to power. So what I'm doing is I'm hitting on the power button, but there is nothing. Uh, okay, so let's do this. Remove it. Just hold the power button. Hmm. Okay, so this is not. This is a no power. So that was just okay. So as we see, let's try it again. The first time we did try, we saw that there was okay. There's a fan spin again, but the fan doesn't seem to transition into a posting mode. If we observe the fan, the pace of yeah, that's it. The pace of the fan is just okay. That is fine. Pretty much the device is not starting. The next thing we want to do is let's see what we have on our PP bus. Let's see, 8.6. Okay, 8.6 tells us that the SMC is doing its job in terms of um, allowing PP bus to move from 8.23 to 8.6. That is good. Okay, so let's see what we have. Source. We have our source rail. Okay, source rail is present. Let's see, it's a machine in SS. Okay, so the machine is actually in SO. So because this coil that we see, okay, let's open up the board view and the schematics. You guys have an idea of what we're doing. This is going to be an 820-00165. It's a 2015 2017 MacBook Air 13 inches. It's okay. That is the board. It's the board view. Okay, so let's go to the other side. We measured at this coil here, which is L7520. L7520. It's an S. The voltage here will only be present when the device is in SO state. So what we have confirmed is that the device is in SO state because we have 5 volt. We have 5 volt on that. So this is this inductor here, L7520. That it's an S. It's sitting on an SO rail. That inductor is sitting on an SO, and then we can see that we have 5 volt. So this device, the board is partially in SO state. So what we mean by partially is in SO state is the device, the board is partially in on mode. So the device is on, but it's not fully. All of the required power rails are not present. So the next thing we want to do is we want to disconnect the charger and then take out the board and find out exactly why it's doing that. So one or more rails on the board may have been affected, which is why the device is behaving the way it's behaving now. So the next thing we want to do is we want to take out the board and find out which rail has been affected and which component is the cause of that. I'm looking out for the magnet. Where is it? Where? Okay, let's check out the screws. So while disassembling a MacBook, while you're disassembling a MacBook Air to take the board out, you do not necessarily have to remove the battery. However, for conveniency, I like to remove the battery because that gives me a better view, or that gives me a complete view. That gives me a complete view of the device. For example, sometimes you may have corrosion here. If you leave the battery, that will be covered and hidden away from you. And if you sometimes if you have a corrosion here, and also which would pull down a particular critical power rail, what will happen is the device will misbehave, and you may not really know that that is coming from corrosion on the trackpad and the trackpad cable. So I like to make sure that it's sticking out. And also when you're putting the device back together, you have better room with the battery not being there. So I just like to make sure the battery is out. But then it's not a requirement to remove the battery. But I like to make sure the battery is out, and people that and the people that work with me, I also like them to do the same thing because otherwise, I don't see the point of if you disassemble the machine because you needed to have a better look inside of the machine. I don't see why you should keep the battery in place because by doing so, you are limiting yourself to what you see. Okay, so and then another thing is so with the screw here. So what I like to do is I make sure this is disconnected first, and then while I'm disconnecting the Wi-Fi cables, the Wi-Fi antenna cable. So I make sure that I don't pull because please zoom into this. So I make sure I don't pull this so that I do not break. I make sure I don't pull. So even while I'm using my tweezer, I'm using my tweezer at the metal part of it. You see, not here. So I'm using my tweezer here, and then I also support it with my fingers like this, so that I do not pull it. So it's very important that this doesn't break because when that breaks, for example, the device can work with only one connected. However, what's going to happen is you will have poor connectivity in terms of your Wi-Fi signal. So. So that is that, and it's also very good to know which screws go where. For example, all of these screws now they may all look the same, but the sizes are not the same. Some are longer, and then some are shorter. So now the screws are out. Now we're disconnecting our cables, and then I always say in terms of using your tweezer and disconnecting cables, make sure your tweezer serves the purpose of your fingers, and do not allow the tweezer to work independently because that way you have no control over it, and then you may damage or damage or pull up a component without you even knowing because you are not in control of the tweezer. uh, phone later. So, okay, that is done. Then the next thing we want to do is let's flip the board over because we can see here there's nothing that basically picks the eye. Next thing we want to do is let's flip the board over and see what could have been the issue. Okay, let's again dust the board, and okay, let's test the board, and that will give us a better view of what is happening.
Side brother.
So again,
Side brother.
I'm gonna call it. Uh, okay, so if you guys can see, so this you see here, there's a bit of a corrosion here. There's a bit of corrosion there. There's a bit of corrosion here. So the spots that we're identifying now, what we want to do is we want to find out what what signals are at those spots and if those signals have been affected. So pretty much this must have been exposed to some kind of liquid. Okay. Okay. So so what we want to do now is we want to check what that resistor is for. We want to check what this resistor is for that section. We just want to be sure that everything here, everything there is fine, and then we want to check that everything there is also fine. So for now, these are going to be the three sections. It's going to be one, uh, two, also 5 volt, 3 volt. This also, and then that, and then that. So now let's see what let's start from let's see what this is. Yeah, so let's go to, so that is the section of the SMC. Now let's come here. So that resistor that we saw is going to be this, which is R5100. So that is going to be SMC reset L. So that is going to be a resistor that pulls up SMC reset L signal. So this is supposed to be 3.3 volt, and that so 3.3 volt is going to be present here, and that also is going to be present here. Now the device is not in reset mode, because if the device was in reset mode, we will not have 8.6 here. We will have 8.2, 8.3. Let's just confirm that again, and also that is not a problem. So if you look at this SMC reset L, we can measure SMC reset L. It's supposed to be 3.3 volt, so we can measure that at this here. So we can measure SMC reset L here. So let us see what we have. Um, see, so basically, what we are doing is we are checking, but definitely SMC reset L is not our problem, because if it was SMC, if that was the case, we will not have fan spin. If that was the case, we will not have 8.6. We'll have 8.2, 8.3. So yeah, so definitely SMC reset is not our problem. So I'm just going to show you guys what I mean by that. So you see that we have in 8.6, not 8.2, and here we also see we have 3.3 there. That's it, 3.3, 3.4. So that is not our problem. Now the next thing we want to look for is here, this section here. So we don't have a problem. Yes, we will address that to avoid problems in future, but that is not our problem now. I don't know if you understand what I'm saying now.
Yeah.
So yes, we have a concern here, but that is not our problem. So we're moving out from there, and TPS. Okay, so let's not worry about this because most of the rails that will come from that, I believe, will be present. Yeah, as 5 volt. Let's not worry about that. Now let's worry about this. Let's see what is happening here. So let's come here. So E7400. Now that section, this section here, and then also you guys will notice that now that I have power connected to the board, I can no longer use my tweezer. So now this section here, let's see what is that section. So we see there is a resistor here that's been affected, and we have a pad there, and then there's also supposed to be another pad here. So I will let me bring on board for you guys to have an idea of what's happening there. So now, this is what, so there's a pad here and there's a pad there. Now, if you look here, the pads seem to have been corroded. So now, as you know, pad, it's very important because if you have a broken pad, it means you may have a broken rail, correct? And then when you have a broken rail, then the circuitry will not do what it's designed to do. So now, first thing first, let's identify what is that resistor for. That resistor, what is it for? So that is the resistor. So it's supposed to be a feedback for our for our RAM circuitry, which is DD-Reg 1.8 volt. Now let's see how this and this. Let's see what's happening there. So let's first check what we have on pin 2 of that resistor. We're supposed to have 1.5 volt. Let's see if we have 1.5 volt. Let's see. What do we have? Okay, so as you guys can see, we have 0.1. That is a problem. So it's supposed to be 1.8 volt, correct? And how do we? The reason why that is just show you guys that. So because you see, it's a 1.8 volt rail, so it should be 1.8 volt. But in this case, it's giving us less than 1.8 volt. So that is a problem here. So now we see we are having 0.9 volt. Let's put it to 20 volt. Let's try it again. What do we have? 0 point. So that is low. So we should be having 1.8 volt, not 0 point. So now let's see. Let's check the pin 1 of it of the same resistor and see what we have. Let's see what we have. We should be having 1.8 volt. So let's see if we can measure that on our capacitor, which is C7415. Why? Because C7415 and R7415 are sitting on the same rail. Do you understand? They are sitting on the same line. So if we want to measure, we can also measure from here. So because if we place our probe here on this cap, it's more as though we're also placing our probe here. So the reason why we're not placing our probe directly here is because the resistor itself is corroded. Yes, you can see that. So what we want to do is we want to see if we have 1.8 volt at the beginning of the resistor. Let's see that. As you guys can see, we have 1.8 volt at the beginning of the resistor. However, at the output of the resistor, we have, okay, now it's 1.15, 1 point, yeah. So basically, it's not supposed to do that. So the next thing we want to do now is we want to remove that resistor and remove the resistor and then address that section of the board. So that resistor will have to replace it, and then not just that, we also make sure that that pad is also healthy. I'll show you guys the pad that I'm concerned about now. I think I did show you guys before, but I'm going to show you guys again. Now, so one, two, so if you guys see this pad here, that's the pad that I'm concerned about. Okay, so as you guys can see, that is indeed our problem because there was no proper communication on that section, which is why the resistor was getting lower output. It's trying to clean that. So I need to clean that in a way that I will have my pad reviewed so that I can solder back a resistor at that. So okay, and it's good enough. Okay, the next thing I want to do now is I want to put solder at that spot. Okay, now I need to put solder there. Okay, so there. I need to get an. I need to use the other soldering. I need to change this the tip of the. Okay, so this soldering iron is not. I need to get another tip for the soldering iron. I need to get another tip for that soldering iron. Otherwise, yeah. Okay, so that is the next thing we're gonna do. Since the section is prepared, now we wanna transfer the resistor. Okay, so that it's done. Resistor is in place. And then, so this is not our issue, but let's just remove that cap because it doesn't look good. That's not an issue though, but this doesn't just look good. Let's just replace it because we don't want it to be an issue in future. So it's not an issue now. Also, this the pull-up resistor SM series yeah. So you see, that is not an issue now, but that's definitely going to be an issue in future. As you guys can see, yeah, yeah. So that's definitely something. And usually, when I have an issue with a pad here, so if you have an issue with this pad, you can always use a different pad to pull it up, to pull the signal up, and you don't have to. That's in case where this signal is this pad here it's having issue. You can use a different. So usually, what I would do is I will use for SMC reset L. So when the signal is when that's I can use that, I can just come here to use it. Just pull it up here and then I'm good. But in this case, I think it's still fine, so I can still use it here. Okay. So now the next thing I want to do is I also want to make sure my pad is prepared. Before I can I definitely need to change the tip of this iron. So it's just gonna waste my time. Slow down. Work. Okay. Okay, prepare the pad. Now we can put that resistor, get it from a donor board. Let's also give the SMC a bit of a reflow, just in case there is any accumulation of dirt underneath the SMC. And again, right now, that is not our problem, really. And also, let's also swap out this resistor here, because that might be a problem in future. Swap that out. Okay, that is out. Okay, that is done. The next thing we want to do is we want to wipe the board, because we do not want flux lying all over the board. It's not a good practice to have flux lying all over the board because you worked on the board. You always want to make sure that you wipe the board after you are done working on the board. So yeah, so we definitely need to test to see if there's if we have changes. But while we're waiting for the board to cool off, we just rather use that time to clean off the board. Definitely, if there's more work that needs to be done, we can always do. Yeah, because I mean, it would make more sense that you clean after you have tested. Yeah, but just so that while we're waiting for the board to cool off, we just use the opportunity to wipe the board. And now it's finished. Okay, remind me tomorrow so we can get a. Okay, so the board is clean. So now give it a bit of a dust and now confirm the healthiness of our line. So let's go back to the section that we had issue with, which was R7415. Let's see what we have now. Okay. So first thing first, let's see if the board still starts at all. I mean, it could be that the board is no longer starting because of maybe the SMC must have, because we did reflow the SMC, maybe there was no proper reflow on the SMC. But let's see if the board still start. Uh, okay, that's a good thing. The board still start. The next thing we want to do is now let's see what we have. Initially, we had 0 point something volt at that section of the board. Let's see what we have now. First, let's see our 1.8 volt at the beginning of the circuitry. Yes, it's there. And then the other side of it, exactly, now we have 1.8 volt. So that's exactly what we're expecting. So let's just see if we have uh, an Apple logo, which we were not having before. And also, by the way, you can also tell from a posting board from the way the fan reacts. So usually I would look at the fan and I will be able to tell what the board is posting. So, okay, now let's see if we have an Apple logo. Okay, that's it. That is an Apple logo, and the machine is loaded. So that is a successful repair. That is about it, guys. As you guys can see, we had a couple of corroded spots on the board. We had to identify which is which, and then obviously the reason why we sent our attention here was because we found there was an issue here because we had a 1.5 volt at the beginning of the circuitry, and then at the end of the circuitry, which is here, we were having less than 1.8 volt, and then we know for sure that we're supposed to have a 1.8 volt in that section, and so that was, and then the other section that we found corrosion, for example, the SMC section, the SMC reset L, R5100, because we didn't, that was not our primary issue, like I explained, so we didn't really worry about that. But even at that, we still had to replace that and also replace the cap for E7501, which is C7501, just so that it do not fail in future. And we also replaced we also replaced R7611. So that is it, guys, and this is a completed repair. I'll see you guys in the next one. Thank you, guys.